little handout here. Fewer people make it. So I created this handout as a summary of what you should know about Chapter 3. So by the time we finish, so we'll get to this later on today. But the advantage is you have page numbers from your textbook noted for each of those questions. So as you go through and you might be wondering, well, what do I need to focus most on? This is it. So as we go through, you want to take a look at these questions. Some of them, you should be able to answer already. By the end of today, you should be able to at least have an idea of everything, at least all the way through page 78. So we'll get into this as we go through a review of Chapter 3 later today. So just summarize everything. So I'll post that in D2L as well. So we left off talking about anaerobic energy production. So we have two systems, the phosphagen, and what's another name for the phosphagen system? Something, yeah. Alphabet soup, ATP PCR system. But it's referring to the same thing. So we have one reaction. It's the quickest avenue for regenerating ATP. And so we call it the alactic anaerobic system. So why would we call it alactic? Not quite. Hold on to that thought. Alactic would mean that it does not. The end result is not lactate. So the other anaerobic system, the fast glycolysis or glycolytic, does. So it's the 11-step process. Hi, Ashley. So the end of which is not pyruvate. We go beyond pyruvate. Mitochondria are working at maximal capacity, and so NAD needs somewhere to deposit hydrogens because it wants to keep participating in glycolysis. So rather than dropping off the hydrogens at the mitochondrial membrane, NAD hands the hydrogens to pyruvate, which then becomes lactate. And so lactate is not the problem, it's just a temporary substrate, which is usually converted to glucose or back to pyruvate, and we'll talk more about that today. So in terms of acidosis, we talked about old view versus new view. We'll get to that in a moment, but I want you to recognize that with acidosis, what we're talking about is an excess amount of hydrogen ions. So that determines the acidity of the cells and the blood. When you have excess amounts of hydrogen ions, the pH is going to drop. That means conditions are becoming increasingly acidic. Our body does have natural buffers and reactions that neutralize some of these hydrogen ions. In fact, the phosphagen system, the one reaction for the phosphagen system is called the creatine kinase reaction. And so in this case, creatine phosphate is the phosphate donor. So creatine phosphate phosphorylates ADP, and so then we go from ADP back to ATP. And in that process, we consume a hydrogen ion. So as long as ATP breakdown is equal to ATP synthesis. Hydrogen ions are in balance, and the pH stays the same. So physiological pH near 7, 7.4, something like that, stays about the same. But as soon as we start breaking down ATP really fast, faster than we can rebuild it, we're going to have a surplus of hydrogen ions. And so with that surplus, if we exceed the buffering capacity of the cell, so this is one avenue for, we could say, I don't know if I would say buffering, but neutralizing. We have other proteins, other ions, bicarbonate ion and so on, that bind to hydrogen ions, but nonetheless, as we exceed the buffering capacity of the cell and we start to accumulate these hydrogen ions, we start to enter an increasingly acidic state where muscles have a difficult time contracting. So it's the hydrogen ions that are the true problem in creating acidosis. So really, if we look at old view versus new view, regardless of whether you like the old view or you like the new view, regardless, it's still the hydrogen ions that create the problem. That's still the foundation of what acidosis means. It's the excess hydrogen ions that we're unable to buffer or neutralize. So over time with training, we get better at buffering. We get better at neutralizing, so we don't fatigue as quickly. Lactic acid or lactate, whether you go with the old or the new view, is not something that hangs around in the muscle and does all of this damage over several hours. It's something that's removed very quickly. Within about 30 to 40 minutes, we're back to a baseline state. So it's not anything that we need to do workouts specifically to clear the lactic acid. So that's a myth that's been promoted for several years, but it's not true. What we do is some damage to muscles with working out. That's what produces muscle soreness and so on. And so we do recovery methods, not to clear the lactic acid or the lactate, but we do recovery methods to increase blood flow, and that facilitates repair of muscle tissue. That helps the immune system. The immune system is kind of the cleanup crew for damaged muscles. So muscles are damaged, the immune system goes in and cleans it up, and then we rebuild muscle better than it was to begin with. The lactate or lactic acid is just kind of a temporary energy substrate that once we are into a recovery period, it's converted back to oxidative substrates that enter the mitochondria, and things pretty well proceed just as normal. So I think it's important, and it is noted a few times in your textbook. This book kind of walks a fine line. I can imagine people reviewing this textbook. Usually when textbooks come out, they have reviewers that make recommendations and things. And this author walks a very fine line between the old view and the new view. She acknowledges the old view, and then she acknowledges the new view, and kind of skirts around the debate. Does that very well. But irrespective of what view you like, it's still the hydrogen ions that are the problem. And if we're breaking down ATP at a very fast rate, which is what we do in high intensity exercise, that's going to be the primary source of these hydrogen ions. So our body's job is to try and neutralize those. And so the whole point is we get better at doing that with training. So do you have any questions on that? Questions?
So the new view is not like 100% proven yet? Is that what you're saying? Or is it just some people are stubborn?
In any field, you find things that evolve over time, opinions and so on. I find that more and more, especially because I've looked at other exercise physiology textbooks, more and more the shift is kind of getting over here,
Okay.
especially as the old guard is retiring and the new, younger people are kind of, I like this view over here. So, regardless though, whether you like old view or new view, it's still hydrogen ions that really create the problem. So I don't know, I'm not sure if it's really a debate, because in the end, it's still the hydrogen ions that create the fatigue. So, all right. Okay, so for lab this week, I decided that we'll be doing the Margarita Kalaman stair step power test. So for lab, please initially meet in the 132. We'll go through an introduction, go through procedures and so on, and then we'll walk over and there's two staircases over on the west side of the liberal arts building that would work really well with 20 feet to run up and before the stairs begin. So we'll do that this week. Last year I wanted to do it, waited too long, and then we got kind of into the poor weather and didn't get a chance. So I wanted to make sure we did that this year before we get into poor weather. So that'll be this week. So we watched that video, remember, last week? So it's a 20-foot approach, and then you're going up 9 stairs, taking 3 stairs at a time. And it's the time between when a foot touches the 3rd step and a foot touches the 9th step. So you're moving your body weight a certain vertical displacement in going from the 3rd to the 9th step. And so you're taking your body weight, you're taking the vertical displacement, and then also taking the time into account. So it's something that you can imagine. In this example, it says 0.65 seconds. It's less than a second. So generating momentum in your start so you can get a good drive up the stairs is going to be really important. And it's important that we also practice with, because we don't have the contact mats that are really fancy and give you time, so all we have is stopwatches. So we're going to have multiple people taking times, and so that's a little bit of a learning curve in starting the watch right when a foot hits the 3rd step, and then stopping the watch when a foot contacts the 9th step. So we're hoping the watches are all in agreement, and we'll take an average and then get your power. So there's a nice normative table that you'll compare your power values to in watts. So another test in a few weeks coming up, the Wingate test. And so with a Wingate test, we have some really nice software, and you'll get an output like this. And 3 of the key measures with that include peak power, mean power, and your fatigue index. So the peak power is something that usually happens within the first 5 seconds. So your muscles have a small amount of ATP stored, and plus you're getting just maybe a little bit of the phosphagen system in there as well. So that kind of, the peak power kind of represents your phosphagen efficiency. Beyond that point, you can see the pedal revolutions, the 5-second totals. So you can see as we gradually go through, the very last 5-second segment from 26 to 30 was 5.5 revolutions for this person, whereas their peak over any 5-second period was 10.25. So almost dividing their output in half between the first part of the test and last part of the test. So from my experience, it's very, very difficult, especially if you're a very anaerobic oriented type of athlete, very difficult past 10 seconds to hang on to that power output. Your ability to hang on to power output is reflected in the mean and the fatigue index. So the peak is just as high as you can be. That's within the first 5 seconds. The mean power is over the course of the entire test. So not just the first 5 seconds or so, but over the course of the entire test, what's your power output? And then the fatigue index takes into account how powerful were you in the first 5 seconds versus the last 5 seconds. So I've had some more endurance type athletes that you make a graph, so time is on the x-axis, power is on the y-axis, and they don't have very much of a drop between the first part of the test and the last part of the test. So why would that make sense for an endurance athlete?
I'm used to having to sustain.
They are fatigue resistant, yeah. So what type of fibers do they have? Slow twitch. But in absolute terms, what's their peak power like? Not real high, not real impressive. Their ability is not in generating a big blast out of the gate. Their ability is in maintaining over the course of the test. So they don't really have an impressive peak power, but their ability to hang on all the way through the test while giving maximal exertion is what is impressive about them. So we'll get to that in a few weeks when we get to our Wingate test. Different methods of assessing blood lactate, because blood lactate is indirectly reflected by hydrogen ion accumulation, isn't it? So what that says is that, okay, so if your blood lactate is high, that also probably means hydrogen ions are starting to accumulate, which is what produces acidosis. So lactate is just kind of a convenient measure because hydrogen ions are more difficult to measure. And so lactate appearance in the blood is reflective of that glycolytic emphasis. So we can look at lactate production, that's the appearance in the blood, versus clearance. So the balance between production and clearance is what you're measuring in the blood. So all of you will do that Wingate test, and you'll get a blood lactate sample before the test and then after the test, and typically you have to wait about 7 minutes after the test because lactate is produced inside the muscle, and so it takes a while for lactate to be shuttled out to the blood where you can actually measure it. So we don't see peak blood lactate values till about 7 minutes after the test. So a resting lactate value might be something like 1 to 3 millimoles per deciliter, whereas following a Wingate test, you might be up around 14 to 15 millimoles per deciliter. So the highest values that I've seen in the literature were up around 20 or 21. So that's people that are very good at buffering would have very high values. So over the course of training, as you become more effective at dealing with acidosis, you're going to also see higher blood lactate values because you can extend for a longer period of time before you fatigue. So you can see methods here. In our lab, we use the finger prick method, and we have a lactate analyzer that looks at an enzyme that correlates with blood lactate. Also the earlobe, I won't make you poke your earlobe, but that's also used in some cases. So on your question sheet, there's one question here I want you to look at. So, okay, so question 11. No, it's not that one. Let's see. Oh, question 8. Question 8. I'm sorry. So it is question. Oh, I'm sorry. Actually, there you are. So, question 8. According to the classical viewpoint, lactic acid is the product of the glycolytic pathway. What happens to 99% of lactic acid at physiological pH near 7? So it dissociates to lactate and hydrogen ion. So that's what acids do, is they dissociate and release hydrogen ions. So what is the term used to describe the balance of appearance and clearance of lactate? So you can see up here on the slide, the balance of appearance versus clearance is called turnover. So that's the key word that is being asked there. So the balance between appearance and clearance is called turnover. So this is a nice diagram that kind of gives you all the avenues for lactate clearance. So in other words, this is how we get lactate out of the blood. And again, it's not the lactate that's creating problems, it's just an indirect marker for excess hydrogen ions. That's what's creating the problem. So oxidation, transamination, this is why I held off on protein metabolism till this chapter, because we're going to talk about it. Gluconeogenesis, do you remember that word? What does that mean? Gluconeogenesis.
Creating ATP from non-glucose sources.
That's very close. That's very close. Somebody chip in. What do we got? Gluconeogenesis. Making glucose from what? Yeah, non-carbohydrate source is right. Here's a new word. Glyconeogenesis. So what do you think that one means? Not creating glucose, but creating what? Glycogen from a non-carbohydrate source. So there's lots of G words that are involved with metabolism. And sweat. So how many of you thought you could actually have some lactate excretion through your sweat? So that's interesting. So all the avenues for production. So why is it that we produce lactate? Well, the overriding reason is this very last one, insufficient oxygen, but that reason ties into the other 4. So we'll talk about each of those individually. So just so you know, when production exceeds clearance, what's going to happen to lactate in your blood? It's going to go up. And that's what we measure is when there's an imbalance between production and clearance.
And that's what's called
Turnover, yes. Okay, so lactate production depends on muscle contraction. So when we contract muscle, we release calcium. So calcium is stored in muscle in what's called the sarcoplasmic reticulum. So with the nerve signal, we get release of calcium, and calcium binds to regulatory proteins that initiates this contractile process. Calcium also has a role in glycogenolysis by activating the enzyme glycogen phosphorylase. So that's interesting. Calcium activates glycogen phosphorylase, which causes the breakdown of glycogen. So we're breaking down glycogen to get glucose for glycolysis. So high glycolytic activity, so that's those 10 steps, results in the production of lactate regardless of whether oxygen levels are sufficient. So that's interesting. So we're kind of taking that step further. So at the beginning of the semester I said if oxygen levels are not sufficient, then we produce lactate. What this is saying is that that's technically mostly true, but not always. So if we're getting a lot of glycolytic activity, lots of glucose that's coming through these 10 steps, eventually the mitochondria are going to be working overtime. And they're not going to be able to take any of the pyruvate. So what do we do with the pyruvate? Got to have something to do with it. So we convert it to lactate. Enzymes, lactate dehydrogenase. So there's another question on here that asks you about lactate dehydrogenase. It's question number 9. Asks you about 2 enzymes. So lactate dehydrogenase, and if you have the PowerPoint pulled up, I apologize if this is kind of small, but lactate dehydrogenase catalyzes this conversion of pyruvate to lactate. So that's what lactate dehydrogenase does. It's a reversible reaction. So you can go from pyruvate to lactate and lactate back to pyruvate. So see how this arrow has both directions. So that means it can go either way. So pyruvate dehydrogenase is involved in the conversion of pyruvate to acetyl-CoA. So do you remember stage 2 of breakdown of glucose? Stage 2, inside the mitochondria, we're going from 3-carbon pyruvate to 2-carbon acetyl-CoA. So that's what pyruvate dehydrogenase does, is converts pyruvate to acetyl-CoA, stage 2 of glucose breakdown. Lactate dehydrogenase has a very high activity, has a very high affinity for pyruvate. What does it mean for an enzyme to have a high affinity for a substrate? That means it's attracted to it. And so it wants to have that substrate go through the reaction that it governs. So an increase in pyruvate plus NADH plus a hydrogen ion further increases the activity of LDH. So we're getting the buildup of a lot of glycolytic products, and that stimulates LDH activity. LDH wants to convert pyruvate to lactate. So this ties in well with our next factor, which is muscle fiber type. So different muscle fibers have, we could say, different preferences in metabolic pathways. So intuitively, what would you say? Slow twitch fibers like which pathway the best, you think, out of the 3? So we have phosphagen, glycolytic, oxidative. Slow twitch fibers, they like which pathway? They like oxidative pathway. Okay, so they're going to have lots of mitochondria that take in oxygen. So that's why endurance athletes are the way they are, is because they have the ability to process oxygen. So slow twitch fibers, they don't produce a lot of lactate. So on the other hand, fast twitch fibers are different. Fast twitch fibers have very few mitochondria. So because of that, what pathway do you think fast twitch fibers like to produce ATP? So their preference is away from the oxidative, regardless of whether there is sufficient oxygen present. They don't have a lot of mitochondria anyway. So to produce ATP, they're going to rely more on phosphagen and glycolytic. So there's different types of LDH enzymes. So how many of you have ever seen this term isozyme? Isozyme. That just means that for a given enzyme, there can be multiple variants. So for lactate dehydrogenase, there are actually 5 variants of that enzyme. So this is a very important point. The type of LDH in fast twitch fibers is 4 and 5. This type of LDH loves to make lactate. And that makes sense. So fast twitch fibers are really good at making lactate. They love that glycolytic pathway. So we get to the end of the glycolytic pathway and we're at pyruvate. If it's in a fast twitch muscle fiber, what's going to happen to the pyruvate? Regardless of oxygen availability, it's more than likely, because fast twitch fibers have these two variants of LDH, it's more than likely pyruvate is just going to be converted to lactate. That's because that's what it does. It doesn't have a lot of mitochondria to put the pyruvate into. Okay, on the other hand, slow twitch fibers have type 1 and 2. Slow twitch fibers have type 1 and 2. And this is really interesting because slow twitch fibers have lots of mitochondria. So if a slow twitch fiber has any lactate around at all, what's it going to do with it? Remember how I said this reaction was reversible? Okay, so if a slow twitch fiber has any of this lactate around, and because it has type 1 and type 2 LDH, it's more than likely to go this direction. So a slow twitch fiber is going to take lactate and convert it back to pyruvate. A fast twitch fiber is going to do the opposite. It's going to take pyruvate and convert it to lactate. So what's the reason? The reason is because of the type of LDH. That's the reason. Fast twitch has type 4 and 5, loves to make lactate. Slow twitch has type 1 and 2, more likely to make pyruvate from the lactate. So any questions on that part? Does it make sense?
What happened to LDH3?
I don't know. I'll have to look that up. But in this, I didn't see that one in this textbook, but that's a good question. What happened to LDH3? That is a really good question. I'll have to look that up. Okay, so sympathetic nervous system. What's the other common name for the sympathetic nervous system? So parasympathetic is sometimes called the rest and digest. Fight or flight. So if it's fight or flight, your body's objective is to make sure you have sufficient glucose in the bloodstream, because the blood is going to transport glucose to active muscles. So the sympathetic nervous system is going to prompt release of hormones that tend to keep glucose in the bloodstream. And so that's what we get. Epinephrine, glucagon, growth hormone, these are all glucose releasing type hormones. So these three hormones, epinephrine, glucagon, and growth hormone, they work in opposition to insulin. So what does insulin do? So glucose is in the blood, what does insulin do? Takes glucose out of the blood, right? So it promotes glucose uptake out of the blood, whereas these other three hormones promote glucose release into the blood. So you have one hormone versus three hormones. They're working against each other, so to speak. Okay, so what is significant about that? So if you're releasing glucose into the bloodstream, where are we getting the glucose? Where does glucose come from? What's the storage form of glucose? Glycogen, right? Okay, so what happens is breakdown of glycogen results in glucose. You start breaking down glucose, and you're going to have high levels of this glucose 6-phosphate. Okay, so let's slow down. Where does glucose 6-phosphate come? What I'm showing you here are the first two steps of the glycolytic pathway. So glucose undergoes one reaction, and then we got glucose 6-phosphate. So you have lots of glucose 6-phosphate that is beginning to accumulate, that's going through these steps of glycolysis. And so what happens is high levels of glucose 6-phosphate increases glycolytic activity, eventually leading to lots of pyruvate. So what if you have more pyruvate than the mitochondria can take? What's going to happen to it? Yeah, it's going to go to lactate. So mitochondria can only take a certain amount before they've reached their capacity, and we have to do something with that pyruvate. So that's what we get right here. An increase in pyruvate, NADH plus hydrogen ultimately results in an increase in lactate once the mitochondria are overloaded. Okay, so the very last one, this is the one that really relates to everything else, although we know that in fast-twitch fibers, they like to produce lactate regardless of oxygen availability. So when we cross that anaerobic threshold, at the point where oxidative metabolism can't support the activity, we have to have another way of producing ATP. And so that's where we get glycolytic metabolism. So without sufficient oxygen to provide a surplus of ATP to support the oxidative system. And so in this case, pyruvate, which has 3 hydrogens, is then converted to lactate, which has 5. So the reason is because we want to recycle NAD. So once NAD goes through this reaction, and it's free of these hydrogens because it gives these hydrogens to pyruvate to make lactate, the NAD is free again, what's it going to do? Yeah, it's going to go back to that same step 6 of glycolysis. It's just going to keep doing that same thing. Okay, so then a rest period ensues, and all of this lactate that we made is converted back to pyruvate. Things proceed as normal. Okay, so lactate clearance. So we talked about lactate production, why we produce lactate. Let's talk about how we get rid of it, lactate clearance. So taking it out of the blood and using it for ATP production. Oxidation is by far the most dominant process. So let's define what oxidation means. Oxidation, how many of you have heard the term before, I'm sure. What does oxidation mean exactly? I think oxidation. What are we talking about with oxidation?
Breaking down things with oxygen.
Yes, yeah, that's exactly right. Breaking down things with oxidative type metabolism. Okay, so that's the most dominant pathway. We're in a rest period now, plenty of oxygen. Oxygen is sufficient, so now everything proceeds back to the oxidative pathway. Okay, so remember, oxygen is the final hydrogen ion electron acceptor that in the mitochondria that makes water. So the other 2 processes, gluconeogenesis, glyconeogenesis, 10 to 25%, and then transamination is 5 to 10%. So all 3 processes involve movement of lactate, either within or between cells. So it's interesting that cells that produce lactate can transfer lactate over to cells that consume lactate. So we have lactate shuttles in skeletal muscle. So these lactate shuttles, you need to remember, monocarboxylate transporters. Monocarboxylate transporters. So this is how we transport lactate within a cell or between two different cells? So these two transporters, monocarboxylate 1 and 4, they transport lactate and also hydrogen ions. So what we're doing is we're able to regulate intracellular pH. So we're able to bind those protons. Usually what happens is we have bicarbonate, which combines with protons to produce carbonic acid, and then that disassociates to carbon dioxide. And what do we do with the carbon dioxide? We transport it to the lungs, and then we exhale it, right? Okay. All right, so let's talk about what transamination means. Okay, so transamination. There's two different ways that we can deal with lactate that involves amino acids. Okay, so transamination forms keto acids. So that's the first thing. You need to know what a keto acid is. So there's three different things to know here. Pyruvate is a keto acid. Acetyl-CoA is a keto acid, and any of the Krebs cycle intermediates. So you remember the Krebs cycle with all of those 8 steps? All of those substrates, as you go around those 8 steps, those are considered keto acids. So keto acids are different than ketones. Okay, so it's completely different, not related to each other. So keto acids not the same as ketones. Usually the involved amino acid is alanine. So that's important to remember. Alanine is the one that's involved with this transamination. Okay, so I want you to pay close attention because we have 2 different avenues here that involve alanine. So we have transamination and we have oxidative deamination. So let me ask you this to start with. What is unique about protein that is not present in fatty acids and glucose? What element is present in amino acids that's not present in fatty acids and glucose? Nitrogen. Nitrogen. So amino acids contain a nitrogen amino group. Nitrogen amino group, that's NH2. NH2. All amino acids have this nitrogen-containing amino group, NH2. So the difference with transamination, the nitrogen-containing amino group is transferred. With oxidative deamination, the nitrogen-containing amino group is removed. That's the difference. So again, all amino acids have an amino group. This amino group, the chemical formula is NH2. Okay. So in transamination, the amino group is transferred. In oxidative deamination, it's removed. So transamination is usually what happens. Less common is oxidative deamination. So this table does a really good job of showing you what the most common examples are. Okay, so let's look at this generalized. Here's a common. So you have 1 amino acid and you have 1 keto acid. So that amino acid could be, here's a specific example. So we're connecting what we see up here with what you have down here. So you have 1 amino acid and 1 keto acid. So the amino acid is glutamate. Glutamate. So that's what we call a non-essential amino acid. The most common amino acid in skeletal muscle is glutamate. So that's 1, and we have 1 keto acid. Remember what the keto acids are? Pyruvate, right? Acetyl-CoA, Krebs cycle intermediate. So here it is right here, pyruvate. That's a keto acid. So here's the reaction right here. This is transamination. So in transamination, what happens to the nitrogen-containing amino group? It's transferred. Transferred where? Okay, so glutamate's the amino acid, so it has the amino group, right? So it transfers it to pyruvate. So now pyruvate has this nitrogen-containing amino group, and guess what? Pyruvate becomes an amino acid. Glutamate no longer has the nitrogen-containing amino group, so guess what it becomes? It now becomes a keto acid. So we're taking one amino acid, one keto acid. The amino acid transfers its amino group to the keto acid. And so then the keto acid becomes amino acid number 2. So the keto acid becomes amino acid number 2. The amino acid becomes keto acid number 2. Okay, so go through it again. Let's go through it again. Danny, we're going to go through it again. Okay, so glutamate, amino acid. It's amino acid number 1. Pyruvate, keto acid number 1. Okay, so glutamate gives its amino group to pyruvate. So now pyruvate has an amino group, so it becomes an amino acid. So it becomes alanine. The pyruvate becomes alanine. Now glutamate doesn't have its nitrogen amino group anymore, so what does it become? Glutamate then becomes a keto acid. In this case, the example is alpha ketoglutarate. So it's just a transfer. We're taking one amino acid, turning it into a keto acid. We're taking a keto acid and turning it into an amino acid. Does that make sense?
How does that have to do with the clearance of lactate?
Hang on to that thought. Okay, we're getting there. Okay, so over here, this happens less frequently. So what we're doing over here is we're taking the nitrogen-containing amino group and removing it. What do we do with it once it's removed? Well, down here, if you read further, and at this point, all I want you to know is we're taking that nitrogen-containing amino group, and what's the chemical formula for an amino group? NH2, and we're going to convert that amino group to ammonia. Okay, ammonia, the chemical formula is NH3. What do we do with ammonia? Right down here. NH3 ammonia is removed in the urine, so it's converted to urea. Converted to urea. This is what we do most of the time. There's a great section in your textbook about it. This is not as common. Okay, so Courtney's question. Why is this important? Okay, so let's take it 3 locations. We've got muscle, we've got blood, and we've got liver. Okay, so we have 2 different cycles going on here. Let's talk about the first cycle. You remember maybe from chapter 2 there was that word that came up, the Cori cycle? Cori cycle, remember? Okay, so what are we doing? We're taking lactate, okay, from the muscle. Okay, so pyruvate converts to lactate, shuttled into the blood, taken up by the liver. What's the liver going to do with it? Converts it back to pyruvate. What can pyruvate do? Pyruvate can then be converted to glucose in the liver. What's the glucose going to do? It's going to go back out into the blood, back to the muscle, converted to pyruvate, and so on. So it's a cycle. You can see how it just goes around. So if we have sufficient oxygen, we're in a recovery period. With the muscle, what's the muscle going to do with pyruvate? Rather than convert it to lactate, if there's sufficient oxygen, lots of mitochondria, like in slow twitch fibers, we're taking pyruvate and doing what with it? Yeah, convert it, put it in the mitochondria, convert it to our common intermediate, acetyl-CoA, everything proceeds like normal. But what if it's really high intensity exercise? Or what if it's more fast twitch muscle fibers? This is where the Cori cycle comes into play, where we're taking pyruvate to lactate, lactate back to pyruvate to glucose, and we're going around that way. Let me ask you something. Do we make any ATP in going from glucose to pyruvate? Yeah, remember? So we invest 2 and make 4, so what's our net? 2, remember? So this is just that glycolysis, that 10 steps from here to here. We invest some ATP, but we also make some ATP. So high intensity exercise. Okay, so transamination is right here. So remember what we said? We have pyruvate. What was the amino acid? Let's go back. So we have glutamate and pyruvate, right? So pyruvate, glutamate. What's glutamate going to do with its nitrogen-containing amino group? Yeah, it's going to transfer it to where? Pyruvate. And what is pyruvate converted to? Alanine. What is the glutamate converted to? Alpha ketoglutarate, right? So here's your 2 reactants right here, pyruvate and glutamate. Okay, remember? Right here, glutamate, pyruvate. We're just transferring the amino group from the glutamate to the pyruvate to get a new amino acid and a new keto acid. So what's the point of all this? This is called the glucose-alanine cycle. Do you remember from chapter 2 review questions, maybe, where we had the phalig? You remember that word, phalig cycle? That's what this is right here. The glucose-alanine cycle is the phalig cycle. So we have glutamate that's transferring its amino group to pyruvate. Glutamate is converted to alpha ketoglutarate. Pyruvate is converted to alanine. So now where does the alanine go? The alanine can then go into the blood where it is taken up by the liver. What can the liver do with it? The liver can do lots of things with it. Okay? It can take the alanine and convert it to pyruvate, which can then be converted to glucose. Okay, so the liver is an amazing organ because that's where gluconeogenesis takes place. So when you think gluconeogenesis, taking a non-carbohydrate like alanine and converting it eventually back to glucose, that's what the liver does. Okay, so what did we say oxidative deamination was? We're not transferring. What are we doing with the nitrogen amino group? We're removing it. We remove it, and then what do we do with it? So NH2, we add one more hydrogen, which makes what? Ammonia. We convert the ammonia to urea, and then we excrete it right here. So this isn't showing all the steps that you get from back here where they show you what happens to each of the products. But how many of you understand the general idea what transamination means versus what oxidative deamination means? So the whole idea is basically to get more glucose, because glucose is important for the blood, because the brain doesn't have its own glycogen stores. So some of that glucose can go to the blood. Some of that glucose can then go to the active muscles where it goes through glycolysis to make some ATP. So this is all happening during high intensity exercise, okay, where we don't have sufficient oxygen. Okay, so any questions at this point? So how can I help? Anything that I can help you understand better?
So like the point of the transamination and the deamination is just to try to get more
Non-carbohydrates back to glucose, because
Okay.
our bodies love glucose.
Right. So the whole point is just trying to get more glucose.
Yes, because that's what the muscles prefer to use. That's the preferred fuel source. So if we got glucose, then it's a fast way to get energy for high intensity exercise, is the whole point. Okay, So 3 different cycles. Okay, so we've talked about the Cori cycle. Okay, that has to do with lactate. So we got muscle, we got liver. So we're going back from lactate to pyruvate to glucose and then back to the muscle. Okay, we've got the phthalic cycle. And what's the most common amino acid again? Question? Alanine is the most common amino acid involved. Okay, so beyond alanine, and this was on that chapter 2 review, branch chain amino acids. So there's actually 4 amino acids. Alanine's the most common, but then we've got our branch chain amino acids that can be converted to what? Glucose. That's the whole idea, is glucose. Our muscles love glucose. So what are the branch chain amino acids?
Acetate.
That's a keto. That's a ketone, which is good. And I was really impressed on the exam. Almost every single one of you listed all 3 ketone bodies, which is really good. So leucine, isoleucine, and valine. Leucine, isoleucine, valine are the 3. So they're conveniently converted to glucose. So that's the whole idea. Glycerol glucose. Where does glycerol come from? So triglycerides, right? Triglycerides, how many fatty acids in a triglyceride? 3. What are all those fatty acids attached to? It's a backbone. It's a glycerol backbone. So we're using fat-burning enzymes to break off those fatty acids, which then go through beta oxidation. We've got all this glycerol left over. So what does the body do with it? Makes glucose out of it. Where does it make glucose out of it? In the liver. That's right. So can you see how all these glucose, the whole in 10, that's what your body loves, is that glucose. So all these cycles, the whole idea, whether it's fat, whether it's lactate, whether it's amino acids, we're all going to get more glucose. Okay, so lactate clearance. So I want you to take a look here. This is intracellular. What does that word intra mean? Intra. Inside, within. So you can stay within. So in the cytoplasm, how many reactions do we have as part of glycolysis? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We get to pyruvate. Okay. If we make lactate, because LDH 4 and 5, right? LDH 4 and 5 loves to make lactate. So we can take lactate and we can shuttle it into the mitochondria. So this is the first time we've talked about that concept, because we've talked about, okay, pyruvate's going to go into the mitochondria, but we haven't really explored this concept of lactate going into the mitochondria. So that's where you have these, what does MCT stand for again? Monocarboxylate transport. So we can take up lactate into the mitochondria of the same cell. Once it's in there, what do we do with it? Lactate back to pyruvate. What are we going to do with the pyruvate after that? Pyruvate to, what's our common intermediate? Acetyl-CoA. Everything proceeds like normal. Here's NAD. Where's NAD going with those hydrogen ions? Mitochondrial matrix, electron transport chain. So everything comes back to these, eventually to the same steps. Okay, so extracellular lactate shuttle. This is between cells. So I want you to take a look here. This represents different muscle fibers. So SO, that stands for slow oxidative. Slow oxidative. FOG and FG stands for fast oxidative glycolytic. And fast glycolytic. So you've got your fast fibers, got your slow fibers. Fast fibers like to do what with pyruvate, regardless of oxygen? They have LDH 4 and 5, so they like to make lactate. So once they've made that lactate, they can take the lactate and do two different things with it. They might give it to a slow oxidative fiber. So that slow oxidative fiber is going to oxidize it, or in the process of transamination, it might use it that way in some way through that chain of steps. The fast fiber can also put it out into the bloodstream. So that's what we would measure with a finger prick, is when we have the lactate circulating within the blood. So there's organs that like to take up lactate and use it. So the liver is one. So we can take lactate and convert it to glucose, okay? We can excrete it through the skin, but the heart can also take up lactate and use it for ATP production. So you see a couple of different transporters here, MCT1 from fiber to fiber, MCT4 from fiber into the blood, or MCT1 within the fiber in the mitochondria. Okay. All right, so how are we doing on time?
11:30.
Okay, all right. I promise I won't go very much further. Let's try to get through the rest of chapter 3. So, at the beginning of exercise, for about the first 3 minutes, is the oxidative system operating at maximal efficiency? No, it's like warming up your car. So where do we get ATP at the beginning of exercise if the oxidative system isn't at full function? Yeah, phosphagen glycolytic. Okay, so we call that initial period the period of oxygen deficit. So what does that word mean, deficit? Not enough of something, right? It's a deficit. It's a deficit in oxygen at the beginning of exercise. Do we have any oxygen stored in our body that we can use while our bodies are warming up? We have a little bit. Okay, we have a little bit, we could say in the hemoglobin, it's part of blood cells, in the myoglobin, part of muscle cells. Okay, so we have a little bit, but it's not sufficient to completely support it. So during this period of oxygen deficit, not enough oxygen, we have to use anaerobic metabolism. Okay, so then we get up to speed, everything is operating along this nice, flat oxygen consumption for the duration of exercise. What do we call that? Nice, homeostatic type of flat oxygen consumption. We feel like we could go forever, we're feeling great, no fatigue. We call that a steady state. Steady state. Okay, so we can have different levels of steady state. So what if the exercise is higher in intensity? To begin with, it's still aerobic, but we're going along at a faster pace versus up here. Okay, so now we're down here. The oxygen deficit is bigger. That's what this shaded area represents. Larger oxygen deficit. Okay, so that's the beginning of exercise, oxygen deficit. After exercise, we have what we call an oxygen debt. What do we do when we have a debt? Hopefully, if we don't declare bankruptcy. Hopefully our bodies aren't declaring bankruptcy. Maybe we'll after the Wingate. Just kidding. Okay, so what do? We pay it back. How do we pay it back? So after you get done with a series of sprints, is your breathing like back to a baseline state, like when you first wake up in the morning? What's your breathing like? Yeah, heavy breathing. So greater rate and depth of breathing. We're paying back this oxygen debt. So there's a correlation between the intensity of the exercise and the oxygen debt. As intensity goes up, the debt goes up. So more and more we're using this acronym. Rather than DET, we're using this acronym called the excess post-exercise oxygen consumption. So we're consuming excess oxygen post-exercise. So it turns out that every liter of oxygen that you consume expends 5 calories. So that's how we can calculate energy expenditure following a workout, is by measuring your oxygen consumption. So your oxygen consumption right now is a lot different than your oxygen consumption right after a workout, in the post-workout period, the excess post-exercise oxygen consumption. So during this period, we're reloading our glycogen stores. So if we want to reload and store glycogen, we don't want to use carbohydrates. We want to spare carbohydrates and get our glycogen stores filled up. What energy source are we using as we come back down to a nice baseline state? Fat. So this provides a tremendous fat burning effect, the excess post-exercise oxygen consumption. So going back to oxygen deficit, there are 3 things that we do to deal with the deficit until our bodies get up to speed. So first, we have some limited oxygen stores in our capillaries, capillary blood, and myoglobin. So myoglobin, protein inside the muscle cell that carries oxygen. The splitting of stored ATP-PCR. Okay, phosphagen system, anaerobic glycolysis. So fast glycolysis, and we get a little bit of lactate production because we haven't got enough oxygen there for the mitochondria to get up to speed. So this is how we deal with the oxygen deficit for about the first 3 minutes or so. Okay, so after exercise, the period of EPOC. This is a tremendous benefit to getting a good body composition. If you want to improve your body composition, this period following a workout is really, really important. So if you have no orthopedic limitations, no cardiovascular limitations, you're able to work out at a really high intensity, that's really beneficial because you're going to be going through this tremendous period of EPOC afterwards and expending lots of fat calories. So we have a fast component and a slow component to this. Slow component takes fast component takes minutes. Slow component can take several hours. So in putting together this lecture, I included this handout within right here. So the afterburn summary table. So just pulled some quick studies and made a table to show some of these benefits. So the table is organized like this. You have a study, you have the participants, the methods, and then the key findings over here. Really important. So let's take, all of them are good, but this Osterberg from 2000 is really a great study because it talks about hours afterward how your metabolism can be elevated. So what I tried to do more with this is not so much aerobic exercise, but more weight training type exercise. So Osterberg 2000, 7 women described as physically active, lifted weights 3 to 4 times per week. Okay, so this is the experimental procedures. Okay, so they had participants 5 sets of 10 exercises, 70% of 1 rep max, 12 repetition maximum load, and they paired the exercises. So their methods, exercises were paired. So bench press and bent over rows. So how many of you have paired exercises? So it's really efficient, plus less rest period means more intensity, right? Greater metabolic demand and so on. So that's what they did. So high volume, short rest periods, and they were pairing exercises. So you're moving the entire workout. So while one muscle group is resting, the opposite muscle group is working. Does that make sense? So that's how you get this tremendous afterburn effect. So they measured oxygen consumption at the 3 and 16-hour post-exercise time points. So 3 hours post-exercise, the metabolic rate was elevated 13%. At 16 hours post, it was still elevated 4%. So 16 hours afterwards, their metabolism is still a little bit elevated, burning more fat calories. So a 62% increase in resting fat metabolism was noted at the 16-hour time point post-exercise. So exercise like weight training can have a tremendous fat burning effect. And it's not because as we're lifting weights, what are we using for fuel? It's not fat. Phosphocreatine, right? Glucose, right? But it's the period afterwards, the hours afterwards, that's where we're really expending lots of these fat calories. So if your metabolism is elevated for several hours afterward, that can add up. So if you're repeatedly performing workouts throughout the week, you're getting a lot of these excess calories to create that deficit that you need to improve your body composition in terms of percentage of body fat. So I included that, and there are 14 of those similar type studies that provide support for that type of training. So let's go just a little bit. We're almost done with chapter 3, so we're almost there. So causes of EPOC, restoration of your ATP and PCR stores. Doesn't take very long. So 50% within 30 seconds. It's fast. Full recovery within 8 minutes. So your stored ATP and PCR, 8 minutes afterward, you're back to full storage. Not very much. Restoration of oxygen stores. Some of you thought about that. So myoglobin, capillary blood, we have this small storage, 2 to 3 minutes. Okay, elevated cardiovascular respiratory function. Okay, so elevated breathing takes more energy by your respiratory muscles, your diaphragm and intercostals, and so on. Okay, that's a little bit. Elevated heart rate, and so on. Okay, hormone levels. Okay, hormone levels. How many have read about or studied the sodium-potassium pump? Nerve cell. Okay, so it's active. What is in the body? What does it mean for a process to be active versus passive? Which one requires ATP? Yeah, active. So the sodium-potassium pump is a pump that exchanges ions against a concentration gradient, which takes ATP. So you've still got restoration of sodium and potassium in muscle and nerves, and so that takes energy, okay? Not very much, but this is still the fast component. Okay, elevated core temperature. How many of you have ever thought there was a difference between your core temperature and your peripheral temperature? So when you stick a thermometer in your ear or underneath your tongue, is it core or peripheral that you're assessing? So 98.6 is your peripheral temperature. Your core temperature surrounding your internal organs can be 1 to 2 degrees higher. So it's different. Core temperature is in here. Peripheral temperature is usually what you get when you have your temperature assessed at doctor's office or whatever. Okay, so elevated core temperature, that takes time to come down following a workout. Our muscles and internal organs are just cranking like an overheated engine that we're trying to cool down. So that provides a tremendous increase in metabolic rate. For each degree Celsius that the body temperature rises, core temperature, we're talking about core temperature now, metabolic rate increases 13 to 15%. So this accounts for a lot of that slow component. So for a few hours afterwards, your core temperature is coming back down. Okay, lactate removal. Okay, so that's something. Energy substrate shift from carbs to fat. Fat requires more oxygen, so elevated post-exercise oxygen consumption makes sense that you would be using fat as a preferred fuel source as you refill your carbohydrate storage. This is the one, the very last one, this is the one that takes a lot of time. So repair of muscle tissue, protein synthesis, that takes a lot of energy to build new tissue. It's expensive from a metabolic standpoint to break down, to clean up damaged tissue, and to replace it with new tissue. So how important is nutrition during the post-workout period? Really important, right? Okay, so beer and chips, right? No. To have something a little more substantial because it's the construction materials that you're using to build that tissue. Your body is like trying to recover and rebuild. You need to put in some good building materials. Okay, all right, so I think that's probably saturated enough for today. So my goal for Thursday, finish up chapter 3, we'll start getting into chapter 4. Chapter 4 has some what we call metabolic equations. You want to bring your calculator. I'm not going to ask for this. This is for you to have so you know what you need to be learning for chapter 3. So I would suggest you bring this with you to class so you can kind of be looking over it to think, okay, this is what I need to be learning and getting out of these chapters. Any questions? Okay, all right, so some of you I'll see. Again, we'll meet in the lab and then we'll walk over together and for the stair test today.